Welcome to Calculus 1, Chapter 3, Section 7, where we're going to talk about rates of change in the natural and social sciences. And this section is going to take one topic for the most part and apply it to a bunch of different natural and social sciences. Now, I teach this course predominantly for those of you who are in the hard sciences, the physics and biology and the like. However, there are some topics that are in here that are applicable all over the place. This video has the potential to be a long one, so it might be that I'll do this as a two-part, and I will go over some homework problems that I'm going to assign to my students in a part 2. But for the moment, let's get in and have a look at the initial notes. Rates of change. Remember that rate of change is essentially synonymous with the first derivative, dy over dx, rise over run, miles per hour. And maybe the most interesting or unusual thing that happens in this section is when we're talking about dy over dx, and we interpret that as rate of change, what we used to do was we would talk about average rate of change. We would look at the average change in the y direction divided by the change in the x direction. And so that's dy over dx, or y2 minus y1 over x2 minus x1. And we put that into the difference quotient, and then we learned that taking the derivative involved taking your x coordinates and pushing them closer and closer together, and therefore sliding these 2 points closer and closer together on a curve. And as delta x or dx got closer and closer to 0, or we called it an h value sometimes, we ended up with the instantaneous rate of change. And we've seen a couple of different types of notation to indicate that. When we start looking at the different applications of the idea of the derivative and rate of change, one of the ways that we can, or one of the arenas where we look at it, is in physics. And physics provides this relationship that is referenced very frequently. Right under the image of me in the top left corner, you see the equation s equals f of t, and the function s is often used to refer to position. And then what we've learned already in previous sections is that the derivative of the position function gives us the velocity function, and the derivative of velocity gives us an acceleration function. And I've pre-highlighted that in these notes, so we see the relationship between those three. All of those are with respect to time. So what I'd like to do in this video is walk through and look at not all of the examples that are provided in these slides, but I'm going to show those of you who are my students or who have access to Webassign where you can find these notes. And then I want to remind you about access to the textbook, because it would take me a very long time without even writing anything to walk through and talk through all of the examples that are provided in these slides. But if you go through and you look at these slides, or if you go into the textbook, it's very well organized. You're going to need to go old school and kind of learn some of this stuff the way that I learned a lot of this stuff, which is taking your homework problems, matching them up to provided examples, which you're going to see in your textbook, or using other resources that are accessible as direct links while doing your homework assignment, and kind of mimic the process and match up the pieces. But while you're doing that, don't just do it with the end goal in mind of getting right answers. I'd like you to do it while you're trying to recognize the pattern and the similarities between the different types of problems and the different steps that you're going through in order to arrive at your answers. It's going to be a challenging one. It's a little bit mind-bending as you're relating what's happening in the original function to what's happening in the derivative, and sometimes what's happening in the second derivative. So I've taken some notes that are reminding me that the first thing I want to do is pop over to Webassign and just have a look at where the resources are located. I had a graph prepared in Desmos already. I'm going to pause real quick and pull up Webassign so that we can have a look. So here we are in Webassign. I'm in the student view, so this should look pretty similar to what my students see. And the two things that I want to remind you of are that you have access to an ebook, which is, I can't draw on this screen because it's an active web page, but almost in the center of the screen, right over, the other direction, right over there. Follow that blue band right there, and it'll eventually get to where it says My eBooks. So you can click on that and click into these notes that I'm using were prepared specifically for Stewart's Early Transcendentals 8th edition calculus book. And you can click into here. It opens a new tab for us. This navigation bar on the left-hand side, there you go. To the right of where it says My Name, there's a little double arrow to the left that if you click on that, it allows you to collapse that navigation bar so you've got access to the whole book. We're in chapter 3, so I'm going to click on differentiation rules. And it should put us to the first page of, oh, I've already been moving around in the book. So I was looking at section 9. In the top left corner under where it says differentiation rules, there's a little triple dot hamburger kind of situation there. If you click on that, it gives you this chapter's part of the table of contents. And since we're in 3.7, I'm going to come down here and you can see the different subtopics that are in there. So there are examples based on physics and chemistry, biology, economics, other sciences. And under other sciences, it says what I was just saying at the beginning of this video, which is that there's a single idea involved in this section, and it can be applied to many, many different fields of study. The other thing that I want to look at with you is, so I'm going to close that tab so that it closes the ebook. And then I'm back sort of on my home screen here, and I'm going to scroll down, and near the bottom left it says Resources. I'm going to click on that. And then I want the resources for this ebook. And I've only made available certain sections to my students, and we're in chapter 3, so I'll click on that. And I can go down here to section 7, and I click on that. And it's going to pull up a PDF of the slides that we're looking at. So you can go through and pull some information. I don't want to view or download those again because we're already looking at them. But you can go in there and see these examples played out. Or you can find similar and sometimes identical examples in the ebook, just with usually more explanation in the ebook than you're going to find in the slides. All right, so please use those resources in order to complete your assignment, or use those resources to supplement your ability to, or your other resources to complete your assignment, because these problems get a little involved. And let's see. All right, so let's talk through this physics example, which is example number 1. Then we'll look at example 2, then we'll go to example 8, and we'll see how long that's taken and whether or not we're going to look at some additional problems here from a homework assignment, or if we'll go into another sort of part 2 video. So here we're being given a position function, s equals, it's a function of time, it's a cubic, t is measured in seconds, position s is measured in meters, and we'd like to find out all of these things. I've already forgotten what the first thing is because I'm overwhelmed by the fact that there are these other 5 things that we're supposed to find. So just looking at problem number 1 is going to be a pretty decent sized conversation. So part A, we're seeing that the velocity function is the derivative of the position function. So all we had to do here was take the first derivative of position in order to arrive at velocity. So that is a function of time. 3t squared minus 12t plus 9. Part B is asking for the velocity after 2 seconds, which means the instantaneous rate of change of position. In other words, velocity. In order to find the velocity when t equals 2, we simply take the number 2 and plug it into our velocity equation. So we're evaluating v of 2. In other words, the derivative of the position function with respect to time evaluated when t equals 2. You see the arithmetic happening there for a final answer of -3 meters per second. A velocity that's negative means that your object, or whatever it is, I would say typically, just like on the xy coordinate plane, negative either means you're going left or you're going in the downward direction. If you run into a word problem where you're going to have negatives, it's somewhat frequent that you will see a note that tells you how to orient your positive and negative. It'll put in parentheses, it'll say something like, assume up is positive. And I think we actually see an example like that as we go along. To find the velocity after 4 seconds, we plug in the number 4 into our velocity equation. You see the arithmetic, we get 9 meters per second. Part C asks us to, the particle is at rest, right? So when is the particle at rest? In order to find when a particle is at rest, right, this would go on a flashcard. How do you find when a particle is at rest? That question would go on one side of your flashcard. On the other side of the card, or note card, or whatever, or if it's a Quizlet or what, I don't care. On the other side, it would say, find your velocity equation, maybe by taking the derivative of your position equation, and then set the velocity equation equal to 0. So certainly a particle is at rest when it has a velocity of 0. In this case, we took a position equation, which was a third-degree polynomial, a cubic. We took the derivative. We got this on the left-hand side, second-degree polynomial, and we're factoring it and setting it equal to 0. I don't love the way that this was formatted. If it were me, I would have put this on the left-hand side factored. I would have put this on the left-hand side factored, and then I would have set it equal to 0 and realized that the left-hand side equals 0 when either t minus 1 is equal to t minus, that didn't work, minus 1 is equal to 0, or when t minus 3 is equal to 0. And that happens when t is equal to 1 or when t is equal to 3. So I don't love the organization of the arithmetic on this one. However, it does boil down to the fact that when t equals 1 or t equals 3, we have a velocity of 0. Therefore, our particle is at rest when t equals 1 or t equals 3. So again, find your velocity equation, set it equal to 0, solve for t. Those are the t values when your particle is at rest. Part D wants to know when our particle is moving in the positive direction. A particle is moving in the positive direction when its velocity, its change in position with respect to time, is greater than 0. Flashcard, right? Take the derivative of position function, get velocity function, make sure or figure out when it's going to be greater than 0. In this case, we have the velocity function already. It's been factored. You could take this and divide both sides by positive 3. That would get rid of this 3. And how is it, remind me, how is it that I'm supposed to figure out when the left-hand side of this thing is greater than 0? You could think of it this way. It's true when both of those factors are positive or when both of those factors are negative. Often the way that we are taught to do this in an algebra class is you take the number line and you make note of where this expression is equal to 0. And we figured that out in the previous part. That was when t equaled 1 and when t equaled 3. And we're trying to determine, now that's when it was equal to 0. We want to know when it's greater than 0. So if you test a t value to the left of the number 1, and if you test a t value that's in here, and you test a t value that's in here, you'll be able to determine whether, and when I say test, I mean pick a number, pick a number, pick a number. One at a time, test those numbers in this expression and see if it makes it greater than or less than 0. What you should also probably know, but maybe you weren't taught to think of it this way, is I often like to think of it in a visual way. The graph of this thing is a parabola. It's a quadratic. And look at that 3 in front of the t squared. Does my parabola open concave up or concave down? And of course, since the 3 is positive, it opens concave up. And does that parabola have x-intercepts, or in this case, t-intercepts on the horizontal axis? Absolutely. And where are those intercepts? Those intercepts happen when you have y values of 0, or in this case, v of t, velocity values of 0. And when does that happen? When t equals 1 and when t equals 3. So look at the right-hand side of your screen again. I'm going to draw the parabola. Now looking at that parabola with the blue axis as the t-axis, as the horizontal axis, you tell me, where is that parabola greater than 0? I'd say this part that's sticking up above the horizontal axis here, and this part that's sticking up above the horizontal axis here. That's when the velocity is greater than 0. In other words, look at the bottom of your screen. In other words, when t is less than 1 and when t is greater than 3. Those arms that are sticking up above the x-axis. That's when you have velocity values that are greater than 0. So you could certainly guess when your particle is moving in the negative direction. It would be between, literally between, t values of 1 and 3. And that's answered here. Nice. So bringing the algebra forward into a calculus class. Not bringing a lot of pre-calc, not bringing a lot of trig with us, but the algebra is still here. All right, part E. Use the information from part D. We can make a sketch of the motion of the particle back and forth along the line. Now, if we assume, sorry, I'm moving these slides all over the place. If we assume that this s-axis is moving positive in the right-hand direction, and we remember this information up here in the top right, we said positive motion where our t values were less than 1, negative motion between 1 and 3, positive again after t equals 3. What happens before t equals 0? You can't go back in time. So we're going to say that t equals 0 is kind of our starting point. And when t equals 0, our position is equal to 0. How do we know that? Take a t value of 0 and plug it into the position equation, s of t. We get 0. And then after 1 second, that's where we're changing from moving in the positive or right-hand direction to moving in the left-hand direction. So you see, literally, we're making a U-turn here where position is equal to 4. We know that position is equal to 4 there because we took a t value of 1 and plugged it into our position equation. Then we moved in the negative direction between t equals 1 and t equals 3. When we then made another U-turn and started moving in the positive direction again. And that went all the way off to the right because there were no constraints placed on our t value. We sort of assumed that t was never going to be less than 0, but there was no upper bound on the t value, so we just let this thing go streaming off to the right. And that is our schematic sketch. Sounds so official. Oh good, there's a part F. I almost forgot. because of what we learned in D and E, we need to calculate the oh, right. So we're calculating the total distance traveled. Now, if you can imagine a golf ball is a good example. So if you hit a golf ball that starts on the ground and you hit it well, the thing flies up into the air in this big arc and then it lands on the ground again. It starts at a height of 0 off the ground and it finishes at a height of 0 off the ground. So would you say that vertically your golf ball has traveled a total vertical distance of 0? Well, the distance between 0 and 0 is certainly 0. The reason why that happens is because some of the time the ball was moving in the positive direction, upward, and the rest of the time the ball was moving in the negative direction, downward. And so we're not really accounting for the up and down flight path of the ball when we look at simply its beginning and ending height above the ground. The same thing's happening in this problem. We have some positive motion, then some negative motion, and then some more positive motion. So we need to take those different segments into account. And so that's what's happening here. The positive motion was happening between 0 and 1. Let's put a big plus sign under that. Negative motion was happening between 1 and 3. Positive motion again happening between 3 and 5. Really, the positive motion we said keeps going for larger and larger t values, but we're going to cap it at 5 at this point. And because I'm sure that was the call of the question, like 6 slides back when we saw f for the first time. So the distance traveled in the first second, so between time values of 0 and 1, the total distance traveled is 4 meters. And how did we figure that out? What is this f of 1 and f of 0? The position equation was originally described as s equals f of t. That was their way of telling us that position, literally, position is a function of time. All right, so that's what these f of 1 and f of 0 are. We're calculating position. And the difference between 4 and 0 is 4, great. And then from 1 to 3, look at this, the difference in position values, 0 minus 4 is negative 4. And that's why we've put the absolute value bars on there in order to switch the sign on that value and interpret it as, how should I say, we're taking direction out of this numerical value negative 4. The negative really tells us direction. It's moving in the negative direction, or it's moving to the left, or it's moving down. But we don't care about direction. We're just trying to talk about distance. And so by taking the absolute value, that turns the distance that our particle was covering into a positive value. And then from 3 to 5, the distance traveled. This was a positive number anyway, but we're leaving the absolute value bars on there. We get 20, add up our 3 distances for a total distance traveled of 28 meters. The act of taking some of our domain from 0 to 5 in this case for our t values and chopping it up into segments is something that we're going to see also later in the semester when we reverse all of this. Instead of taking derivatives, we're going to find antiderivatives, and we're going to be doing integration and finding area under curves and things like that. And there will be instances where we need to chop up the domain into bits and pieces and be doing some absolute value in order to add things together where we're letting go of direction. I don't think I've ever gone this far in the alphabet in terms of subparts of one question. We're up to G. The acceleration, this was a question about acceleration, and acceleration is the derivative of velocity. So we started at position, took the derivative, got velocity. Take the derivative again, we get an acceleration function. Second derivative of position, first derivative of velocity. Our acceleration equation is 6t minus 12. The acceleration at t equals 4 is, Take the 4, plug it into the acceleration equation. You see the arithmetic, and we get an answer of 12 meters per second squared. Acceleration is distance per unit of time squared. And in H, we were asked to graph the velocity, position, velocity, and acceleration curves all on the same graph. You're welcome to do this on a graphing calculator, and if you do on a graphing calculator or in Desmos or some other application, I recommend doing what was done here, which is changing your window dimensions. And the first one of these that I would make sure that you set your x-axis or your t-axis, your horizontal axis with a minimum of 0. You could maybe set it at -1 or something, depending on the scale of the whole thing, but starting it off at 0, since we're not going back in time, would be a good idea. Capping it at 5, and this value of -12 ended up allowing the acceleration curve or line that you're seeing in green here. It allowed it to stay mostly on screen. That -12 probably could have been pushed down a little bit lower, maybe -15. The +25 allowed the velocity curve to pretty much stay on screen the whole time, all the way out to this x value or t value of 5. That's just something that you're going to have to play around with. I'm going to do that and adjust some of those kinds of settings. You saw that graph that I had in Desmos already. We'll go in and we'll tweak those settings. I'll show you how to do that in there also. If you're using a graphing calculator and you're not familiar with how to change the size of the window, the 25, not the zeros, well, the 0, yeah, you can change that too, the -12 and the +5, do a search for a video on how to change window size on whatever kind of calculator you have, TI-84 or whatever. There will be a quick window, just the push of a couple of buttons. We're up to subsection I, okay. I don't even know how many letters that is. So we've made it up to I, and the question is, the particle speeds up. So when is the particle speeding up? The answer to that question is, come back, there it is. The answer to that question is, the particle is speeding up when your velocity is positive and your velocity is increasing. In other words, when v and a are both positive. And we're going to look at this graphically. You could be accelerating in the negative direction also, which would require your velocity to be negative and your acceleration would want to be negative. And seeing those things graphically so that you can see those numbers simultaneously is pretty helpful. Let's see. Do we see the graph again? We do. Oh, this is a nice illustration. So from left to right, let's look for speeds up. So our particle is speeding up when, let's try the highlighter here. Let me just take this up and through here and up and through here. So you can see that the green line, which is the only line here, the green line is below the t-axis. So acceleration is negative on that green line. And the blue curve, which represents velocity, is also below the t-axis between a t-value of 1 and a t-value of 2. Anywhere outside of that interval, either your velocity curve goes above the t-axis or your acceleration line goes above the t-axis. So that is where we are speeding up, but notice it says backwards here, so we're accelerating in the negative direction from t equals 1 to t equals 2. Where else are we speeding up? We move to the right a little bit. So we're also speeding up from where t equals 3 to t equals 5, and that is because on that interval, our acceleration line is above the t-axis and our velocity curve is above the t-axis. So acceleration and velocity are both positive, means we're speeding up in the positive direction. When they're both negative, it means we are accelerating or speeding up in the negative direction. Slowing down means we have to have sort of opposites on those. So if our velocity is positive, but our acceleration is in the negative direction, then we're slowing down. If our velocity, so that happens in here, from 0 to 1, and we are also slowing down if our velocity is negative. There's our blue curve. If our velocity is negative, but our acceleration is in the positive direction. So we're trying to use this in terms of what you would do while you're driving a car would be a little bit weird, because going backwards at any kind of rate of speed and then accelerating in the positive direction typically amounts to applying the brake. Okay, applying the brakes is definitely accelerating contrary to your current velocity. You're either taking your positive velocity and making it lower, or you're taking your negative velocity and making it lower or closer to 0. So you're moving it towards 0. All right, I'm not going to talk about that anymore, or it's just going to get more muddled in your mind. But this is a really great illustration and the kind of a thing that if you're using a graphing calculator, transcribing those graphs onto a piece of paper, drawing some lines on there, maybe using some colored pencils, would be a great way to get right answers to questions that are similar to these. Okay, so example number 2 is strange. This is something that is, right, velocity and acceleration position, I can relate to those. This is a type of problem that's fairly common in this section. And what we have here is a rod or a piece of wire that is homogeneous, so it's made of the same stuff and kind of evenly distributed through it. If you have a piece of wire or a rod that's homogeneous, then its linear density would be uniform, sort of evenly spread through, as though you'd stirred your ingredients together very well before making this rod. And that linear density would be defined as the mass per unit length. So the maybe it's a kilogram per meter worth of rod length that you have. Suppose, however, that the rod is not homogeneous. So we did not stir our ingredients together well before making this rod, and that its mass is measured from its left endpoint to some arbitrary endpoint x. And the mass from the left endpoint here out to, imagine we're going to be cutting off a length of this rod. So we start measuring from the left end of this thing, and we're going to cut it off at some point, x. Or in a moment, we'll cut it at x1, or we'll speculate, what if we had cut it at x2? What if we had cut it at both of these points and just were looking at this segment? Okay, so that's sort of what's happening here. The mass is going to be described or modeled using a function. Mass is going to equal f of x as measured from the left endpoint. So if I wanted to know the mass of just this portion of the rod, I would have to calculate m of x2 minus m of x1. That would be the mass of just that length of the rod. Here it is. So this is what I was just saying. The mass of the part of the rod that lies between x equals x1 and x equals x2 is given by, we're going to call it delta m, change in x. It's weird the way that the notation kind of keeps getting dragged forward. Delta x or delta m, change in m. but it is exactly what I said. They're calling it f of x2 minus f of x1. I called it m of x2 minus m of x1. Just below me, you see m equals f of x, similar to how we saw s equals f of t. That was position is a function of time. Here we're seeing mass is a function of distance from the left end point of the rod. So F is what we're using to calculate the mass of the rod starting from the left end point out to either x2 or x1 in this case. So the average density, now average density is still y2 minus y1 over x2 minus x1. And that's exactly what we're seeing in this average density equation, except our y values are talking about mass, and our x values are talking about distance from the left end point of the rod. Now if we do this, if we compress that delta x value and we send it down towards 0 as this denominator gets closer and closer to 0 as the place where we're making those two cuts in the rod to get closer together, what we end up computing is the linear density at a single point. And we know that as we apply a limit and we send h to 0, or the denominator off to 0, or in this case delta x to 0, what we're finding is the derivative. So the linear density, as x goes to 0, the linear density becomes the rate of change of mass with respect to length. That's either, I would say that's probably going to be modeled as dm dx. There it is, symbolically. The change in mass with respect to the change in our distance away from the left end point of the rod. That's the linear density at some particular point, derivative of mass with respect to length. For example, if our original function describing, let me just jump up here for one moment. Where did it go? Is it that far back? It's not. Sorry, I'm all over the place now. I thought I had drawn a line pointing at it. Well, I'm not finding it. That's okay. So if this is our linear density function, or sorry, this is our mass function, is equal to the square root of x. So x is measured in meters. M is being measured in kilograms. The average density is, so here's y2 minus y1 over x2 minus x1. There's the x2 minus x1, gives us this, so we're calculating average density for a particular part of the rod. And the arithmetic on that kicks out approximately 0.48 kilogram meters. Now the density at the specific point where we are 1 meter away from the left end point of the rod, in other words, where x equals 1, the density there can be found by taking the derivative of, at the top of the screen, m equals f of x equals the square root of x. So we take the square root of x, or x to the 1/2 power, take the derivative, we get 1 over 2 times the square root of x. We evaluate that at x equals 1 because we want to know what the density is right at that point, at that 1 meter mark, and we get 0.5. And it's kilograms per meter. And that's not a surprise that it's kilograms per meter because the numerator is change in mass, which we were told is being measured in kilograms, and the denominator is change in x, where x was representing distance from the left end point of the rod, measured in meters, so kilograms per meter. And that's it for that one, but just conceptually I wanted to talk through it with you because it's weird. A number of the rest of these examples are weird also. This one is talking about electric charge moving through a wire and electrons, and you're going to be looking for, we start out talking about average current, Q2 minus Q1 over T2 minus T1, and if we take that denominator and send it off to 0, so we're taking the limit, what we end up with is instantaneous rate of change. The current thus the current is the rate at which charge flows through that surface, measured in units of charge per unit time. Coulombs per second, otherwise known as amperes. And there's a chemistry example, and so on and so on. What I want to do is jump down to example number 8. So I'm going to pause instead of subjecting you to all of the scrolling, and I'll see you at example 8. And here in example 8, it's a little bit of a switch away from some of the harder sciences, I guess you would call them, or natural sciences. Economics would put us into the College of Business, maybe instead of the College of Arts and Sciences. Example 8 is talking about a cost function. Now, I talk about this with my students who are taking a business calculus or elementary calculus course. And we start out with a cost function, and the same thing has happened in all of the examples that I just skipped over. The initial conversation is about change in y over change in x. Whatever y and x represent, whatever variables are being used that are different, or if it's not x values, it's t values. It's not y values, it's position values or mass values. Here it's a cost value. And cost is what we're looking at in the numerator of this difference quotient. And in the denominator, the x values represent number of items produced. All right. And we sort of just switch our notation a little bit here so that we can incorporate that delta x or a lowercase h value, and we send that off to 0, and we end up with a derivative again. So we over and over and over again in these notes, we make this transition from average rate of change to instantaneous rate of change. And then we interpret instantaneous rate of change as pertains specifically to that problem. In this case, the derivative of a cost function gives us what's called the marginal cost function. Now that's change in cost as a result of change in number of items produced, which is a little bit strange because when you're talking about electrons, you're talking about an exorbitant number of electrons passing through a very skinny sort of cross-section of wiring. If you're talking about a rod that's being cut, you could conceivably cut that into various lengths. It doesn't have to be 1 meter worth of rod or 2 meters worth of rod. It could be 1.86794, right? You could cut it down to the millimeter if you wanted to. So to the thousandths place. But when you're talking about producing units, producing number of items, you don't usually produce some fractional number of laptops or cell phones or personal flotation devices or something. I don't know where that came from. So this is a little bit interesting because dx in the denominator, you're not really going to squeeze it down super close to 0. It's never going to be 0.000001. The farthest we typically squeeze it down in this type of an example is down to 1. That's the smallest number of units that we can come up with without smashing it down to actually be 0. So if we take delta x equaling 1, and now you know why it is that they're doing that, and you produce a fairly large number of items, so that normally that denominator is some extraordinarily small denominator, which with a numerator of 5 would cause this huge difference to exist between 0.00, a trillionth in the denominator and a 5 in the numerator. Simplify that, you get 5 trillion. But with a denominator of 1, you would need 5 trillion to be in the numerator in order to have that same ratio. So that's why we're being told here also that let's take n, the numerator, to be fairly large. So we're scaling this thing up. So the delta x is small compared to n, great, which gives us this. So the first derivative is equal to, or approximately equal to, this is y2 minus y1 over x2 minus x1. N plus 1 minus n equals 1. So there's an invisible denominator of 1 under this thing, which relates us back to here. So dx is the 1 that we talked about. In other words, or as a result, the marginal cost of producing n units is approximately marginal cost. Remember, in this context means first derivative of the cost function. The first derivative of the cost function of producing n units, in other words, instead of marginal cost, convert it to, or think of it as, rate of change. The rate of change between producing n plus, or between producing n units and producing n plus 1 units. That rate of change is approximately equal to the cost of producing that n plus first unit. Because again, you're taking the cost of the nth unit and the n plus first unit, you're finding the difference between them, and then you're dividing it by 1. So you're literally calculating that numerical value, the difference in cost of producing the nth to the n plus first unit. When you subtract them, you get the cost of producing just the n plus first unit. Why would that ever be valuable? Well, you compare that to the revenue generated by selling the n plus first unit, and then you do revenue minus cost, you get profit, and then you can determine if your profit is a positive number or a negative number. Clearly, that's valuable. So you need to do this kind of analysis for cost and revenue so that you can apply it and look at profit overall. It's often appropriate to represent a total cost function as this polynomial. A represents overhead cost. The other terms represent other things that might change in unusual ways as your production increases. You end up adding more personnel, more air conditioning, more electricity, renting additional buildings, and so on. So let's look at an actual example. Here we've got, now imagine that you produce 0 items. This term would go to 0, this term would go to 0, and then you'd still be left with 10,000. You produce 0 items, and it still costs you $10,000 to have your business? Sure. You still have to pay employees and rent and electricity and water and insurance and all these things, right? So that's overhead, is that 10 grand. The marginal cost function is found by taking the first derivative, so that puts us here. And the marginal cost at a production level of 500 items is $15. Remember that if we interpret this based on the conversation that we were having just a couple of minutes ago, what that really is, what that $15 really represents, is the cost of not the 500th, but the cost to produce the 501st item. It's that move from 500 to 501. Now, the actual cost of producing the 501st item, if we found it by simply not using the first derivative, not by plugging 500 into the marginal cost function, C prime, forget about plugging 500 into there, which we just did and got 15.00. If we just put 501 into our cost function and 500 into our cost function, calculate, do the subtraction, we end up getting $15.01. So in actuality, to produce that 501st item would cost us $15.01. So those two different ways of calculating that change only approximately equal because of the nature of the problem and that delta x can't be made super, super small. The smallest we could make it was 1. Wow. And just think, we skipped the biology example and the electricity example and the thermodynamic, whatever the other examples were. This one's just dipping into business, and it's still fairly complicated, and you're seeing a discrepancy there now. Take 500 and turn it into 500 million items produced. All of a sudden, you're going to want to take the more exact examination of the cost to produce those additional items. We're at the 50-minute mark, so I'm going to go ahead and stop here, and I will see you in part 2, where we'll go through and look at a couple of additional example problems. See you there. Oh, and you'll be able to click, where is it? Right. Yeah, click that right there. It'll take you right to that part 2 video. See you over there.